Thank you very much, Professor Hill, and it's an honor to be invited to give this keynote talk. So yeah, as it just been introduced, I will speak about experimental diagnostics for gas solids fluidized beds. So the focus will be on experimental diagnostics and state-of-the-art such, and especially the ones that we have been working with. But I will start my first section of my talk first with a short introduction of my background and the Chalmers connection to fluidized bed technology, and also a few slides on modeling and the different modeling approach for gas solids fluidized beds, because there are a few outside CFD, but also within CFD, and they attempt to solve different questions and describe them in different ways, and they have a need for experimental work, which differs depending on which modeling you are. So I would like also to initiate this talk with some reflections on what is the interplay that we would like to see between experimental work and modeling work. So first, just as I just said, some short introduction of the link that Chalmers has to fluidized bed technology. It's been an important part of Chalmers and of this division, the division of energy technology. We see here in these pictures already in 1981, this means more than 40 years ago, we installed a bubbling fluidized bed boiler, 16 megawatts. So this is commercial scale. And this was installed the very same year that Sweden approved the first carbon tax in the world. And then, of course, many district heating operators chose to move then from fossil fuels to biomass. That's when fluidized bed technology was identified as a good technology, suitable technology for burning biomass, but still there was no much research on agglomeration, for example, and so on. So a lot of the research in biomass combustion has been done in this boiler, in this BFB. This boiler served as district heating to the university campus and also to the surrounding part of the city in our campus. So it's operated on a commercial basis. And this fact makes that it's operating on a regular basis. It provides revenues, benefits, and part of these benefits then can be used for research campaigns and research projects. So that is some concept that we have really been satisfied with, that we are able to run a unit which from design stage was meant to be a research unit with a lot of probe samplings, but at the same time is able to sustain itself economically. In '89, we also installed a CFB boiler, 12 megawatt this time. This one is still standing and still in use. And in 2007, the CFB boiler was completed with bubbling fluidized bed gasifier 4 megawatt indirect gasifier. So there is a strong link between Chalmers and fluidized bed technology. Chalmers is also placed in Gothenburg, Sweden, and Gothenburg is the cradle of Valmet boilers. So it's one of the main manufacturers, actually the main one for biomass boilers. And they had the very first workshops here in Gothenburg, and they are still there. So there is a strong link to fluidization engineering here at Chalmers. Our group started experimental research from the installation of the very first boiler in '81, but we started with modeling also in 2003. That's where I started my PhD, and I had this interest also in modeling. So then we started to cooperate with industry and develop models for fluidized bed combustion mainly, but now we have been extending those to cover other fluidized bed applications than just combustion. Okay, with the short background, here will be the points that I will go through in my agenda, the different sections. First, as I said before, I would like to talk a bit about modeling. That's not the focus here in this presentation, but I would like to link to modeling. Then I'll talk about fluid dynamical scaling, something that we have been using a lot in our activities here, and which we found extremely valuable. And then I will dive into different experimental techniques, which are not on the shelf, so to say. They are advanced, I would say. And they need development, but they are able to provide information which is otherwise not attainable by classical techniques used. So let's start with the first section. It's about modeling. Here is a diagram which I really love. It's from Finland, Lappeenranta University. And here they classified different modeling approaches for fluidized bed. And they divided this in the space and time dimensions, depending on the resolution of those. And here we can see the different types of modeling. I will just activate my pointer. Here we go. Yeah, so we have the most resolved modeling, like direct number simulation. This is a particle scale, and then we would enter then discrete element modeling here. We lose resolution. We are not resolving at the same scale as direct number simulation. And then we would go into still CFD, Eulerian descriptions. And when we leave these domain of solving the momentum equations, then we start entering the domain of empirical and semi-empirical models, where we don't solve the momentum equation. We still close mass and heat balances, but we are able to save a lot of computational time by skipping the momentum equations, the closure of the momentum equations. Of course, that comes at a cost, and the cost is that we don't solve the velocity fields, and we need to obtain them by other means. And finally, we have also 0D models, black box models that you would find, for example, you would employ in process modeling softwares like Aspen. So this is a nice view, I think, but I would like to add one dimension into this, and it is the need for empirical input. The more you simplify, if you don't solve momentum equations, for example, if you remove spatial dimensions, the more you do this, the more you need to compensate with empirical input. So this is an important aspect to take into account, that there is always, at any of these, there is always a need for some level of empirical input. And this changes depending on where you are in this figure. So this is what we will today, or that I will speak about today. Which techniques do we have at hand to provide this empirical input? If we go to the different types of modeling, and we class CFD as the type of modeling that solves all of these balances, mass, energy, and momentum, then we have a lot of softwares. One of the most known is ANSYS. That's a commercial one, but there are other ones which are open source also. And here, still today, I would say the main challenge is in the closure, the formulation and closure of the momentum balances. And that's still a research field in itself. And again, the more you simplify, I would say then the most simplified version of CFD is this Eulerian approach, the more you need then to compensate with some kind of empirical input, like for the subgrid models, for example. So, in a summary, I would say the focus here is most often used by researchers, this kind of approach, sometimes by industry to solve specific problems or issues. And the computational cost related to other types of modeling is high. Then we have the semi-empirical model I was discussing or just presenting about. We solve mass and energy balances, but not momentum balances. So what we do instead is to substitute those closures of momentum balance with empirical knowledge or some assumptions on the velocity field, for example. With this, we can reduce the computational time drastically. And we have done such a model in collaboration with a boiler manufacturer. It's a 3D model, and it's about 500,000 cells typically that is solved in a couple of hours. And this is still used in research. We still use that model in some of our research projects, but mostly in collaboration with industry. And the main advantage is that it is a low computational time, and also that it's mainly interpolative. This means that this empirical information that we provide helps the reliability of the model results, since typically simulations are within the scope of the empirical data that we have used. So that's interpolative. It's not as generic as a CFD model would be. You put them there to use results which are outside the scope of the empirical data you have used, because it's not based on first principles, but it's very practical if you want to do interpolative modeling. And finally, we have a simplification of this semi-empirical variant, which is 1D instead of 3D. Why doing that? Well, because industry sometimes wants these models which are at a very low computational cost. This is fractions of a second. And this allows them to put these in dynamical simulations, for example, of process simulations and so on. Again, one main difference between the two is that CFD is based on first principles, and it has more reliable generality of the formulation, while the semi-empirical modeling depends a lot on which experimental data you have used. So here is an example. You cannot these are two boilers. This is a typical large-scale boiler. I think it's about 220 megawatt, placed in the US. I think is this one. It's one of the boilers we have been modeling. And this small one here at the corner, this is the Chalmers 12 megawatt CFB boiler I was presenting some slides ago. So as you see, it's unreasonable to use empirical data right off taken from the Chalmers boiler and expect that it would work in this other geometry. It's different geometries, it's different conditions, different scales of turbulence, so everything changes. So that's where is the problem with semi-empirical modeling. It's crucial to have a wide scope of measurement data, or it's a wide scope of the empirical input that you provide in this modeling. That's why in our semi-empirical modeling, we've been covering scales from the 12 megawatt out up to 500 megawatt in order to have a wide scope. So the semi-empirical modeling requires then validation. These are measured oxygen concentrations at 200 megawatt boiler. This is a measurement campaign at 19 meters above the grid. This is oxygen concentration field. So it was about 30 measurements, and then we could reproduce this oxygen concentration field, and then the one produced by our model. And with this, of course, then we're able to fit different parameters like gas dispersion and so on. So this kind of data is needed for the empirical modeling and fitting of those. For 1D, then what we need is to have data, experimental data from the process. So it's process data, typically heat flows, heat and mass flows of the steam and so on, so that we can calculate enthalpy heat flows from the furnace, for example. So in here, we introduce our model this is in Modelica, but there are other formulations, other softwares too. So we substitute typical boxes. Some of the commercial codes have a fluidized bed box, but that's designed for chemical reactors, and they are not describing boilers properly. So we did our own box for a boiler, bubbling fluidized bed boiler or circulating fluidized bed boiler, that then we can introduce in a steam process, on a steam cycle, and see the interplay between the furnace and the steam side. So this we did in another project. But then, of course, to validate this, you need site data of flows, pressure, temperatures of the steam site. Well, and this is the last slide. I think it's probably the most important in this presentation. No numbers, just words, but I think still it conveys the main message I would like to give. And it's that we always should look for an iteration, synergetic iteration between modeling and experiments. So if we start with this iteration, is that typically when you develop a part of your model, a sub-model, you have a theoretical hypothesis on how things should work. And then based on that, you need to define which kind of experiments do I want to carry out in order to confirm or discard this hypothesis. So these are targeted experiments. These are experiments in which you attempt to extract specific information about a specific parameter. So this is working at a specific level. When you have this new submodel, you can put it into your whole model and then run your large-scale simulations. So the whole model with momentum, mass, heat transfer for everything, where your new developed module is included, and then validate this against large-scale experiments. So here we have another iteration. And based on this, on the agreement or disagreement of these simulations and large-scale experiments, then you need to identify a new knowledge gap. With this new knowledge gap, you need to formulate a new hypothesis to improve your submodel. And this will require new targeted experiments, maybe another variable, another parameter, another phenomena. And then you need to design how would those experiments look like. So I would say this is the optimal way to work when you want to combine modeling and experiments. And it's always a question of what should be first. Is it modeling, and then from this we define experiments, or is it experiments and from this we create an hypothesis and try to describe it through a model? I think it doesn't matter much where you start. The thing is that you should keep doing this iteration indeed. So this is some principle that we try to keep in our work, in our activities when we combine modeling and experiments. So with that, I move on to the next section. That's fluid dynamical scaling. And very short, this is a method that allows us to keep the fluid dynamics in a scaled form at different conditions. So we can have, for example, a large scale hot boiler or any other reactor or device, and we can do experiments at ambient conditions at another scale, typically much smaller, typically non-pressurized, but in a way that if we keep a number of dimensionless parameter constant, we will be able to scale up the fluid dynamics so that we can measure in our scale model, in our cold flow model, and from this calculate what would be that value of that parameter in the industrial conditions, in the large hot conditions. There is a number of several sets of these scaling laws in literature, quite a large number actually, but two of the most used one are given by Glicksman. The first one is the full scaling set of laws. It is very much like that of Fourier also, and it was published in '84. This is here are listed the different parameters. We have the Freud number, the density ratio, we have the Reynolds number for the particles and for the gas, and then the geometric similarity and particle size distribution. We also have flow, the particle solids flux, and that's because this was initially intended for FCC reactors, where this is a parameter that you control. It's not an independent output of how you run the operations, but it's something that you control in your return leg. In circulating fluidized bed boilers, this is not a parameter that you control. It's simply a consequence on how you operate the unit. So we don't use these when we work with boilers. Then a few years later came the simplified set of scaling laws in which the Reynolds numbers for the gas and for the particles are removed and substituted by the ratio, the fluidization number. This is the ratio between the fluidization velocity and the minimum fluidization velocity. So this simplifies things a lot. It removes one parameter, and with this we win 1 degree of freedom. And I will try to be a bit more clear on what I mean here. So in the full scaling laws, combining these, you can combine the Freud number and the Reynolds numbers to obtain this, that the length scaling, so how large will your unit be at the lab compared to the real one, is given by this expression here. So as you see, it's the properties of the gas only. It's the viscosity of the gas at cold and hot conditions. That decides everything. So once you have decided the gas that you're going to use in your lab unit and the pressure and temperatures, then the length scaling factor is given, and that you cannot change. You like it or not. And typically you don't, because this means that the length scaling factors, at least for fluidized bed combustion, they are too large to have units in the lab. They are typically 4 to 5. And if you have a unit which is 40 meters tall, that would mean that you need a scale model which is 10 meters tall. And typically you don't have place and infrastructure for that in your lab. But if it's smaller units, then you could attempt, of course, to use the full set of scaling laws. So there is this restriction that the length scaling is given with the full set. The simplified set opens a lot. We remove one parameter, we win 1 degree of freedom. And how is that seen? Well, again, combining the different parameters, we can end up in this expression that the length scaling factor is the ratio, or is a function of the ratio of the minimum fluidization velocities. And as we all know, the minimum fluidization velocity is function of the gas. So the gas plays a role as for the full set, but also of the solids. So here, the nice thing is that accommodating your solids using different solids, you can decide what your length scaling factor is. And here you have a lot of flexibility. You can go down to length scaling factor from 4 or 5 in the full set for combustion to 9, 10, 13, 20. And that makes it suddenly much more realistic to have lab units. And you can accommodate the scaling factor to the space in your lab and to your infrastructure, how much flow your fans can provide and so on. So it's a very powerful tool. Here is an example of the very first scaling unit we had. It was when the CFB boiler was installed. Then at the same time, this was built, a scale model of that CFB with the simplified scaling laws. And here we see the main consequences. I mean, the circulating fluidized bed boiler has this working temperature, 850 Celsius. At the lab, we have ambient temperature. If we apply those conservations of the simplified scaling laws, we end up in this, typically in this, that we have a much finer bed material. Here is about 6 times finer. And we have also much heavier bed material. This is to compensate for the density ratio. Then the gas gets colder, it gets denser, so the solids need to get denser too. So finer and denser material. This means typically fine metal powders to keep the fluid dynamics the same as at hot conditions. Of course, there are a lot of other consequences. The pressure drop scales too. Superficial velocities, the gas velocities change. Fluxes change, time scales. These scale models go faster than reality. So if you record them and want to get a picture of how is the real flow, you need to slow down the playback of these videos. So this is just an example of typically what we end up with. Then the question is, why is fluid dynamical scaling good? I want to strengthen some of the factors, which I think is very important. It gives increased operational flexibility. We know that when we are measuring in projects with industrial partners, it's difficult with industrial campaigns to tell them how to operate. Now I would like this load level. Now I would like this amount of secondary air. Now you want to change things, but of course, operation is not adapted to your wishes. Typically, it's rather you that measure what is being operated right then. But instead in cold flow models, you can adapt operation and you can operate in ways that would never be allowed in real boilers. So that gives you a tool to explore operations that you would never have. The other is that ambient conditions, if you choose to have your lab model at ambient conditions, enable a wider range of diagnostic tools, which otherwise would be too delicate for these harsh, hot environments. Also, that ambient conditions are safer. Typically, you can perform experiments. 1 people can do that in an industrial site. This means typically that a lot of people have to be there, and there are safety issues. And finally, that they are much, much cheaper also. So these are strong reasons, all of them. I think each of them just by itself make a strong argument for using fluid dynamical scaling. But of course, the nice thing is that the results you get, they are still have the same value in terms of scientific research, but that you're able then with industry to tell them this is what is happening inside your reactor, inside your unit. Good. We had this project with a boiler manufacturer, and we scaled down one of their most best sellers, so to say. And this is what they say. This is typically the CFB boiler we sell the most. It is co-firing biomass and coal. It is between 200 and 300 megawatt. And they said this is representative for our CFB boilers, our portfolio. So we took this one and then we scale it down using these scaling laws I just presented, the simplified set, and that allowed us to use a scale factor 13 so that it could fit nicely in our lab. And then it looked like this in our lab. It ends up being about 3 meter tall in our lab. It's 40 meter in reality. And well, here you see it. This is, I used to say, this is our tallest professor. So this gives you a picture of how tall this unit is. And one key thing here in the design, I just want to point it out fastly, is that, of course, you have solids population balance, both in reality in the real boiler and in your lab scale model. And here it is very important that you try to match the same particle size distribution in your CFB loop. Now, what we did here was to take samples in the furnace, samples in the particle seal, the return leg, because in industrial boilers, the return leg contains typically as much material as the furnace, but they differ very much in size distribution, these solids. So you need to take both and then see what is in total the solids that you are having in that boiler. Then scale those down and put them in your unit. Now, the thing is, when you have scaled the solids down, and this is the inventory you want to have in your lab unit, the important thing then is not to lose them. If your cyclone is not 100% effective, you will modify the distribution that you are feeding them, that you want to have inside. So this differs very much from a cyclone in a boiler. A cyclone in a boiler wants to have a cut size in which fines are not accumulated, because that would be a severe problem for the boiler if the distribution of the solids becomes too fine. So there is an intention of letting the finer go, but in the lab scale model, the intention of the cyclone is to capture absolutely everything, because we are feeding the solids inventory that we want to see inside our unit. So these kind of units at the lab scale, they require extremely efficient cyclones. Good, and here we see these are the samples taken from the boiler, one in the furnace, and then one in the seal, and then we have the one that we were feeding in the boiler. So this is the one from the boiler in average in the middle, and then the one that we have in the furnace and in the seal in our scale model. And as we see, we managed to keep the average that we want to have in between the two, in between the furnace and the particle seal. So this is very important. And here is how it looks then in reality. If I'm allowed to play this, let's see. No, maybe it won't like it. So here we go. So this is when it operates. This is operated with copper particles, fine copper particles, about 40 micrometers. And this is how it looks like. So the first thing you do, of course, is to validate this. Is it working, the scaling, or not? So we took 4 different operational cases from the real boiler, and then we measured the solid concentration profiles with pressure. Of course, we are able to put more pressure tabs in our scale model than there are in the boiler. So we had 4 different cases at different velocities. This is for the highest velocity. I have marked with a red line what is the 1 kilo per cubic meter level. So this is high fluidization velocity. And as we see, as we go down in fluidization velocity, the solids concentration at the freeboard is falling down. But for all 4 cases, the scale model in our lab managed to recreate, to resemble the fluid dynamics in the boiler. And once you have that validation, then you can start doing your research. And what is that research about? Well, you can do a lot of things, and I will talk more about this later. But for example, yeah, this is one thing we can do. This is validation for the Chalmers boiler once upon a time. Again, the solid concentration profile against data from the boiler, it was fitting nice. And then you can start doing research in your lab unit. For example, one thing we wanted to investigate was to introduce a tracer gas, and you introduce it somewhere in the freeboard, and then it will disperse. And then if you put a probe and map the whole lateral profile of the tracer gas concentration, you are able to calculate the gas dispersion, lateral dispersion. So we did this both in the boiler and in the scale model, and here are the results. And as we see, the gas disperses at the same rate in both, after scaling, of course. So with this, you can do a lot of things that are difficult to do in a boiler or costly. Another study is even more advantageous, is that you can change geometry very easily in a scale model. These are made of plexiglass, and if you build it modularly, you can change different parts. So we have along the time change different parts. For example, in the bottom, the taper walls, what happens without taper walls, what happens with the angle of the taper walls, what happens with the inclination of the secondary air injections, what happens with the exit region geometry. That's a quite important question for CFVs, because you have solids flow reaching the top, and then the popular belief, so to say, is that everything, the upflow that you have here in the upper furnace, will make it to the cyclone. But in reality, what we have come up with after measurements is that it's actually just a small share often of this flow that actually makes it to the cyclone. Most of it instead will be recirculated inside the furnace. And that's critical for the design of an operation of CFVs of any kind, because the external mass flow, the circulation of the solids in the loop, that is a design parameter that affects a lot the heat balance closure, the mass balance closure in chemical applications, and so on. So it's important. And what we can do here then is to change geometries easily of this exit to see what is the impact of that in the circulation. This is the backflow, so how much of the solids don't make it to the cyclone, of the solids reaching this upper exit region. And we see that this correlates to the Stokes numbers. For fine solids or light solids, low Stokes number, then all of them go to the cyclone. But as we increase the Stokes number, we see that more and more solids, up to 80%, actually don't manage to follow the gas flow into the cyclone. And of course, that's important. So these are studies that we're able to do. We can also change geometry, and we try different geometrical configurations for that to see the effect of this. Good, then I can jump into experimental techniques. That's the last section in my presentation. I will go through 3 of them. One for particle tracking of individual particles in gas solids fluidized beds. The other one is for tracking of the solids phase, as a continuous phase. And finally, a technique for the diagnostics of the solids flow. So for particle tracking, it's about tracking one individual particle immersed in a fluidized bed. And we have been working with this for quite a long time now. It started pretty much with our projects on gasification. This is our 4 megawatt gasifier. And of course, it's important to know what is the mixing, what is the fate of a biomass particle, in which regions is it located, and what will be the typical mixing, axial segregation, residence time inside the gasifier, and so on. So it's important to be able to know what happens to a biomass particle after it enters such a unit. This was a 4 megawatt, and after this, a 20 megawatt unit, or producing 20 megawatt of synthetic natural gas, was built here in Gothenburg. So these are the very first experiments we did once upon a time. This is 1 meter per second fluidization velocity, and we were tracing wood chips. So what we did was to record from the roof. This is cold conditions. We installed the camera, we fluidized, and then we injected biomass particles, which were made phosphorescent. So with this, I can show you the video. Soon we will close the light here, and then you will be able to see these biomass particles mixing simply. They will advance from right to left due to dispersive and convective mixing. So this is an easy thing. It's not very advanced, not rocket science. From this, we can make digital image analysis and see how they spread. This is the cumulative number of observations. And from this, you can start extracting some statistics. This is what we have, for example, in a scale model. So we did a scale model of this also. And we saw this, that for low velocities, these particles were accumulating in some regions in between the preferred bubble paths. So these are regions with bad fluidization in which particles accumulate. And then if we increase, of course, the fluidization velocity, we'll have a much better mixing with a lot of immersion of the particles inside the bed, and where you can hardly guess where the nozzles, the preferred bubble paths, are. So this was for a scale model, but we also did this with a camera, a hot probe camera in real operation. So we have the equivalent condition as this one in our boiler. And as you see, it pretty much resembles these accumulation points. While if we go to the 7.5 case, we see that then the mixing is much better. the particles do not float anymore and do not accumulate at certain regions. So again, the scaling is able to reproduce to resemble the real conditions of the mixing. We did digital image analysis also in the scale model of the gasifier. This is how an experiment looks like that provides the data I just shown in the last slide. And then, of course, you can compare, and you can see that the hot and the cold unit provide the same dispersion coefficient. So this was nice to see, but then once you have validated that the scaling works, then you are interested in getting more information at the cold conditions. So instead of just seeing the particle when it's floating on the surface, because we are recording from upwards, we would like to track the particle the whole time. So that's when we started to think of a method. Can we track the particle when it is immersed in the bed also? And that's when we started to develop this magnetic particle tracking. This was a technique originally developed in the US, in a US lab, and then later acquired also by, or developed also by us and by Eindhoven, and now let's say CanMed, I think has also applied it more recently. So the principle is easy. We have magnetoresistive sensors, a number of them. And if you have a magnet in the vicinity, it will create a magnetic field, and this sensor will sample that magnetic field. If you have that, if you put a number of sensors, then you can overdetermine this system so that you can reconstruct the location of a particle. And if you do this dynamically, you can reconstruct the trajectory. So we have tracking in 3 dimensions. Spatial resolution right now is 1 millimeter. We are working to get this better. Temporal resolution can be very high. We choose 200 Hertz. That's enough for our purpose. And then we are also working on reducing the magnet size. Now we have it down to 3 millimeters. So what we do with this is that we insert our magnet inside a capsule. And in that capsule, we can have a filling or not to provide it with the right density, resembling different fuels. So with this, we can get velocity fields, concentration fields, residence time, dispersion rates, and so on. This is a video showing the first validation of the online tracking. We have a pendulum movement, and then we see that we can online recreate this pendulum movement of our magnet. And then when we insert it in a bed instead, this is a bed with 4 sensors, this will be the tracking of the immersed tracer that we have. And then with this, we have worked for quite many years now. We can have a trajectory, and from this trajectory, given enough time to make statistics robust, we can get velocity fields, concentration fields, and also distributions. This is, for example, different types of tracers resembling biochar biomass, and a more denser tracer, and then how they segregate at the surface. The biochar will float mostly, biomass will have some penetration into the surface of the bed, and so on. And if we increase fluidization velocity, the mixing will be much better for all of them. So we have been working on providing this information to modeling in order to create more reliable models of this. Another thing we have been doing then is to look at the momentum transfer, and then we can have different trajectories, and from this have the rheometry of the fluidized bed. So shear stress against shear rate, and study what is the rheology of the fluidized bed. And now we are applying this magnetic tracking to the large scale model of the boiler. I will rush to solids tracing. I will employ 5 minutes more of my time. So solids tracing is purposed to follow a bulk instead of an individual particle. And what we have here is coils, impedance coils, and they will give a signal depending on the amount of tracer, powder tracer that we have. So we insert here a tracer which has the same conditions as the bed material, and then see which signal it gives. Now this unit, what it does is to circulate material. This is not something you can see with your eye, but it circulates material clockwise here. So first it will give signal on C1, and then a peak on C2, C3, and C4. And from this, we can have these signals then on the coils. And as you see, C1, C2, C3, and C4. Now the signal can be used in many different ways. You can create then convection diffusion models to estimate what is the velocity of this solids flow, what is the dispersion, lateral dispersion of the solids flow. This is something we are doing. Also, you can use convolution models to fit the residence time in between two chosen coils, and from that also to develop a tank model for that. And this is something we have done then. For example, between C1 and C2, the residence time distribution would be this one then. So this is something that it's doable easily with these coil measurements. And finally, I will come to what I typically call the jewel of the crown. It's a technique that we have developed in the last couple of years, and it's based on radar. So just a short background is that typical in fluidized bed technologies measurements, tomographic measurements have been based on an emitter and a receiver. And then the signal that you get in the receiver is a function of the integral absorption of the signal through a whole path. And that's been the principle. And then if you have different emitters and receivers, you can increase resolution of this. But in principle, it gives you one value, which is an integral absorption. Now, the radar principle is very different. What it does is that every time it meets solids, it reflects a signal depending on the concentration of the solids that you have right there in that point. So it's a resolved measurement along the beam. Now, the higher the frequency of this radar beam, the more the resolution you will have along this beam. So we have now used terahertz resolution, which give you, or terahertz frequencies that give you resolution, which are sub-millimeter, about 120 micrometers resolution. So with this, we can tackle typical problems. It's non-intrusive. It shows to have long penetration lengths, which is good. So in that way, it is better than, for example, laser. It has high resolution, good accuracy, I will show that. And then we measure at the same time concentration through this principle, but also velocity through the well-known Doppler principle of the radar measurements. And we can have the emitter and receiver in the same device. So we need only one access to the unit instead of two. With this, I will show, this is how it looks like when we employ it. The radar, you see it here, it is pointing at one location in this window, and as you see, the bed is operating. And this is the kind of information, raw data that we get before processing. And finally, when we process, we obtain this kind of profiles. This is the typical profile, solid concentration profile you would derive from pressure measurements. And you see the scattering in the data, while with radar, we have very nice, very continuous profiles. And there is at very, very high concentrations, we tried the limits, and at very high concentrations, there is then a limitation in the penetration, but these are far below the ones at which you operate the units typically in commercial operation. We can also measure velocity profiles, not only concentration. So this is from the top, what is the average velocity for different conditions, different gas velocities. And what I think is most valuable of the whole thing is that for each of these points is an average velocity of the solids, but for each of these, we can break it down into a solids distribution, solids velocity distribution. So we can see how many of the solids are moving upwards and which fraction is moving downwards, for example. So this in a very, very well-resolved distribution. So I think this is very, very valuable, and also at a very nicely resolved temporal resolution, which opens for measuring continuously and with good accuracy and nice spatial resolution, measuring, for example, granular temperatures, turbulences, and so on. This is an example of measurements from the side, and this is a typical profile of concentration, solids concentration, lateral solids concentration for different velocities. As we see, when we increase velocity, the solids concentration increases accordingly. And this is velocity of the solids also. So with this, I close my presentation. There is one more slide with some main messages, 3 of them. The first one would be that properly combined modeling and experimental work are an unbeatable cocktail. That's how I chose to define it, but they are very powerful if you combine them. So modelers and experimentalists, they should meet more often and talk more. Modeling development needs targeted measurements, not only large-scale measurements, devoted to extract specific information from specific phenomena. So we more and more need to think of what we need to measure and find techniques for that. And finally, my main message, I would say, is that for many years, fluidized bed technology has been limited by the lack of measurement techniques accessing some parameters. But now, with the latest development, we have novel techniques that access those parameters. So now we are, I think, on the verge of a new stage where experiments can provide us with that information. So that's, I would say, a new paradigm, I would say. So with this, I would like to thank you all from us all. This is the fluidization group, how it looked like 1 year ago. So some new faces, and some of these are not anymore here. But special thanks to all of these people, and many, many special thanks to the one to the left. That's Carolina Guillo, who is in charge of our lab and our experimental techniques. So thank you, everybody, and please open for questions.